who's from Pomona College in California. And his next talk is going to be about merging art and optics.
Hi. Thank you. Thank you for the invitation. I'm really happy to be here. It's been really fun. I promised the farthest we'll go is a little bit of geometric optics, so I think this is probably a good way to end the conference. It should be a little bit chiller and hopefully some eye candy if the projector works. Before I begin, I'd just like to acknowledge that the work I'm going to present was done on the traditional land of the Tongva people, and the conference here is in the Tohono O'odham land. And also, if you have time, the Arizona Museum is fantastic if you like baskets from the Southwest. All right. So this is going to be work that's actually merging art history, art, and optics. So this is something I could never do alone, and I'm really lucky to work with a great team. The team that I'm working with is Kristen Cunningham, who's a studio artist from Los Angeles, California, and Victoria Lobis, who's an art historian. She was, until recently, at Claremont McKenna College. She just got appointed as the director of the Pomona College Museum of Art, which is pretty exciting for us because now she can start to acquire things that we can use for our classes and stuff like that. The Pomona College Museum of Art actually has helped fund some of this, as has the Hive, which is a creativity center that's shared with the 5 Claremont colleges. All right, so this is not my scholarship. This is not what I do for research. It's sort of a thing that I've taken to pedagogical ideas have emerged from sort of hobbies of this. And it all started when reading this one book, Vision and Art by Margaret Livingstone. So Margaret Livingstone's a neuroscientist at Harvard, and she looks at the intersection of neuroscience and perception and art. It's a fantastic book. You should read it. And a long time ago, I guess in 2008, my department chair came to me, and I was a new faculty member at Pomona, and he said, hey, we need you to teach ID1 next semester. We need somebody to teach ID1, which is a freshman reading course, and we need your decision by tomorrow. Can you teach a class? And I had just read this book, so I was like, sure. Yeah, I could do something. It'd be really cool to do something on light, perception, and art. It sounded really cool. A third of the way into the semester, I realized I only knew one of those words really well, so I sort of winged it for the rest of the way, but I was able to call in for help. But one of the ideas I want to talk about is that, one of the things I've really learned in this class is you can understand all the optics and all the image making of optical systems you want, and you're not even halfway there, because the optical processing actually doesn't start in the brain, it starts in the eyeball. And I want to talk a little bit about that right now. So there's actually processing going on sort of at the hardware of the retina. It's not just some 1 megapixel image that gets sent to your brain and processed there. So to do that, here's just a simple illustration. Again, I'm trying to make things pretty. Just a black and white drawing by Picasso. The white, okay, so what color? This screen's actually a little bit weird, so it's odd. But if this were given on a regular old cheap projector screen, and I asked you, what color is the screen, what would you say? You would say the screen is white, right? And then I'd ask you, and I'd say, well, what color are these lines? Black. How does that work? Is the projector shooting out black paint and putting it on the screen? No. You see black by the contrast between the black and the white. And it turns out that information is processed in the retina. And if you take an example that was done by Eric Kandel in the 70s that won a Nobel Prize, was they put cats in front of a screen, kind of Clockwork Orange style. And when the screen was uniformly white, no signals went to the brain. Uniformly black, no signals went to the brain. But when the slides were taken in and out and the contrast went, there were signals sent to the brain. So the brain's only getting signals of contrast information. It's not getting pure on value level information. Okay? Same thing happens with color, but with complementary colors. So this is actually a photo I took, Ellsworth Kelly, green, blue, red. This is at the Broad Museum in Los Angeles. It's a really beautiful picture. It's a huge canvas painting. Sometimes when I take students to art galleries, we'll look at something like this, and they'll be like, yeah, whatever. Like, I could probably paint that. And technically, yeah, it's maybe, well, it actually is really beautiful technically. But yes, it is just 3 colors. It's maybe not what you think about as a technically great painting. But gosh, it pulls you in when you stand in front of this thing, okay? And I just want you to stare at this for a little bit. It's not going to be as great because I think you're not seeing the true colors. I'm seeing the true colors here. This is pretty diminished because of the monitor. But look at what happens when I make this picture monochrome. The green thing just disappears, right? And this is done in 1963, so I don't think Ellsworth Kelly, he probably had black and white cameras, but he certainly didn't have Photoshop to do this. And I don't think he did this intentionally. So what's happening now is there's no value information. There's no contrast information that I talked about for that processor in your brain getting information on the green square. But there's color information going to your brain from the green square. And that actually, the color part of your eyeball and the black and white part of your eyeball, the rods and the cones, they not only process information on the retina itself, but they send it to different processing centers in the brain. Okay, so, and they're as far apart as, say, hearing and smelling. and they have different functions. So the black and white is sort of your hunter part of your brain. That's sort of locating things. How fast are things moving? If you're going to catch a ball, that's going to be your black and white signal processing that's going to do that. But if you're identifying things, recognizing faces, recognizing objects, that's the color part of your brain that's working. So what's cool is in this picture, you're getting the information that there's a rectangle there. Your brain's recognizing, there's a green rectangle right there. And then your other part of your brain is like, where? I don't see a rectangle. I'm unable to locate it. And that causes it to sort of dance around the canvas and take on sort of some activity that it doesn't normally have. Okay, so remember that. I'm going to sort of now shift gears. So we got about that far in the course, and then we actually started to unpack the Hockney-Falco hypothesis. I'm pretty excited to be giving this talk at the University of Arizona. So much of the work that I'm going to talk about for the rest of the talk is really just an outgrowth of the Hockney-Falco hypothesis. So this is Charles Falco, who teaches here, and David Hockney, a famous painter. At around 2000, David Hockney sort of made this hypothesis, and he was looking at paintings through time, right? So from about 1300 to about 1425, artists were pretty good at getting the perspective, but they had sort of a cartoonish quality to these faces, right? And then in 1430, all of a sudden there was this jump, right? So here's a painting by Campine, and the faces start to take on a much more realistic, much more photographic quality to them. Right? And then a great example of it, one of the masters of this was Van Eyck, a Dutch artist in the 1400s. And this is a painting, I forgot the cardinal's name, but a cardinal who came to the Netherlands. And Van Eyck painted him. And this is the sketch that he made, and then the painting of this person. And that's just almost perfect photographic quality, something you wouldn't have seen 50 years prior to that. And, Hockney has an amazing eye and also a pretty good brain. And he said, I suspect that he was using some kind of optical instrument to get this kind of quality. Right? So the idea is, he probably used some kind of camera obscura, sort of just a lens, actually much like today, the lens that was set up where you could project the image onto the piece of paper. Like, I'll just project the image on the paper and I'll trace it. That's the tracing right here. And then work from that tracing to make that picture there. Okay, that's a great hypothesis. It seems reasonable, but we're scientists. We like evidence, and that's where Charles Falco came in. So this is actually the first piece that he examined. It's a little bit dim, but I'm going to zoom in and hopefully it'll look a little better. So this happy couple is the first painting that, from Lorenzo Lotto, is the first painting that Charles Falco examined. And what he was looking for is, he said, he actually went the other way. So Hockney was like, wow, these paintings have taken on a photorealism. I suspect that you're probably using some kind of optical device. As an optical scientist, he said, well, then the smart way to look for the evidence of an optical device is not to look for how well these things are rendered, but look for the flaws within the optical system and see how they manifest themselves within the painting. Okay, and obviously one of the things that's different about a photograph and a painting, and this gets to neuroscience too, is when I look around this room, because my brain doesn't like me to not see things otherwise, sure, at any moment, I'm focusing on one thing, and that depth there's a depth of field, and certain things are in focus. But whenever I try to look at anything, it comes in focus. So when I observe the room, it looks like everything's in focus, and I can see everyone's face, and I can see everything. But the reality is, if I took a photograph of the room, some parts would be in focus, and some other parts wouldn't be in focus. Okay, that's something that a person in 1500 didn't know. Right? You did not know that a photograph had a depth of field, because they'd never seen a photograph before. So let's look at this painting. You can see in this painting that, the rug that the couple's in front of and the background and their faces are all in focus. So it's true to a painting like that, right? That's what you want your mind, that's what your mind thinks the world looks like, so that's what you want the painting to look like. But let's zoom in a little bit on that rug. Okay, so if you zoom in on the rug, it's a little bit hard to see with this projector, but download the image, you can see it. There's a lot of detail here. So the detail of the pattern on the rug is exquisite, and I don't know if you can see it, but you can see as it moves back, the painter made it blurrier and blurrier, right? This looks like a photograph, and they didn't know any better. But if he was working from a camera, and the camera had this part of the image in focus, it was going to have really sharp lines to work from. And then, as you move back, these things are going to get out of focus. They're going to have to adjust the camera to get the other regions. So at every region in this painting, if I go back, you're going to have to adjust the camera to have this region in focus, then focus here, keep working your way back so that you can render each part of this painting in perfect realistic detail. But of course, as I start to adjust my optical instrument and I start to adjust the object distance, I'm going to start to see, well, first I'm going to see a depth of field, and you're probably not going to, it's going to take a while to do this. You're probably not going to do it at such resolution that everything stays sharp in focus, and he got a little sloppy there. Moreover, if you look carefully, you can in black and white, you can follow the patterns on the rug. And what you can look at is if these are parallel lines, as most painters would have known at this time, parallel lines will all meet at infinity at some vanishing point. And that vanishing point depends upon your perspective of where you are compared to the object. So the lines at the front of the thing that are in focus here are vanishing at a vanishing point that's represented by the blue lines. Whereas deeper in the painting, the parallel lines in the rug further back are vanishing at a different vanishing point. So this is evidence that the camera was focused somewhere here, and then the camera was moved behind that, and there was sort of a blurry region in between that he interpolated, and that's evidenced by the different vanishing points. All right, so if you put this together, this is the Hockney-Falco hypothesis. This is actually David Hockney doing a reproduction of the cardinal. So you have your subject sits on a bright, sunny day. You need lots and lots of light to do this because you're projecting pretty big images that you're going to trace. And then just a curved lens. There was plenty of technology at the time to make a curved lens, a crude mirror or lens, either way. I guess in this case it's a mirror. So the image is cast on the wall, and then the artist traces the image. Right? Obviously, the door would be closed here. The artist would be working in the dark. But from that, you can create an ultra-realistic painting just by tracing. Okay, so now back to the class I was teaching. So we actually read we read the Falco Hockney paper, but we also read an entire book about Johannes Vermeer and his paintings. And this was a writing course. It was actually kind of hard when we were talking about optics and neuroscience to come up with the good essay questions. And the best essay question I think I came up with is this cheating? Can an artist cheat? Okay, and I got some great essays because we have some great students. My personal opinion is, short of misattributing something, I really don't think an artist can cheat. It's really about how the art interacts with the viewer. However you get there, you get there. There's no rules in art about things like that. So that was sort of the essay answer I was sort of looking for, and I got a lot of those. But then I had one student's essay, and I still remember it to this day. She was, and she talked about Vermeer, and here's a picture of a Vermeer, a little bit of a dim picture of a Vermeer, and she said, it's not the perspective of a Vermeer that makes a Vermeer great. She's like, when you see a Vermeer, what is amazing about what he did was he captured light. Just the way that her hood sort of shines in the light and the wine bottle shining in the light, and just this whole room draws you in. It's the colors and the light and the warmth that separates Vermeer and that made Vermeer a master. She's like, I don't care that his perspective was perfect. I mean, sure, it helps. It makes these things look realistic. But there was lots of artists who were doing perfect perspective at a time, but none of them had the vibrance and the color and the sort of realistic, just intensity of the light that Vermeer was able to do. So she argued that, whatever instrument Vermeer used, his genius was in his use of color, and so it's not even a valid question for him. All right, so let's fast forward a few years. I was only allowed to teach that course once. I don't know why. About 5 years ago, a movie came out. So I've sort of always been fascinated by this subject since I read the papers. And I don't know if you've seen it, but the movie's called Tim's Vermeer. And it's a story of Tim Jensen, who really undersells him stuff. He's actually a graphic artist. He has a very good eye. He claims he's not an artist. He's quite a good eye, and he has quite a big brain. And what he set out to do was he set out to reproduce this Vermeer, which is the piano lesson. It's in Buckingham Palace. It's in the Queen's collection, so very few people actually get to see it. But it's one of the 30 or so Vermeer paintings that we have. And, more evidence for Vermeer. Just about all of his canvases are the same size. Just about every painting that he did is in the same salon with the light coming in from there. All the subjects are about the same distance away. So there's a pattern here that if he had a good optical instrument to do these from, he went back to that a bunch of times and kept reproducing paintings from that. Okay, so what Tim set out to do and what he did very effectively is this is his Vermeer. Okay, so he was able to make a Vermeer, and you can see that not only did he make the perspective perfect, which we talked about from Hockney, but he got the colors right too. And I should say, he went all out. He built a room. He put a window in the room. He did it in Texas, I guess, which is a little different than the sun might be a little different than in the Netherlands, but that's not such a big deal. And he only used natural pigments that were available in the 1600s, right? So he made it so that he had to every condition restricting him. Also, he made his own optical devices. So he tried to do it as faithfully as possible, and he captured the colors right. Okay, and if you watch the movie, you realize that he's not just using an optical system. Yeah, he's using a curved mirror to create an image. Okay, but he doesn't just trace the image. And you can't just trace the image and match the colors. So here's the problem. So imagine this. Imagine if I'm projecting we don't need to build a camera obscura or anything like that. Just imagine I have a projector and my canvas on the wall. And let's just do something simple. Let's say I project a red spot onto the wall, and I want to exactly match the red color of that red spot. What color paint do you think I could paint behind that red spot to make that red spot look exactly the same red as it should be? White. The only color that's going to reflect the spectrum equally and make that red light that's shining on the wall look correct like red light is white. So there's no way that I can actually match colors with this just tracing perspectives onto a camera obscura like Hockney's doing back here. Like Hockney's doing right there, right? So I can find the lines, I can find the edges, I can find the regions of high contrast, but I can't match the colors. Okay, so if you watch the movie, he doesn't give the details of how he builds this, but you can sort of back it out if you know a little bit of optics. But the trick he uses is, I wanted to put an optics diagram in here, so I built this one. The object for him is going to be the image from his camera obscura. Okay, so you have an object. So now it's an image really, but think of it as an object. Okay, so that's going to give off light. And then we just put a mirror at 45 degrees. And if we make the distance from the mirror to the object the same as the distance to our canvas down here, we get an image that's inverted, I guess, or rotated from the object, but it's exactly on top of our canvas. Okay, so if I look down at this mirror, anywhere the mirror is blocking my view, I see the object, and immediately next to it, I see the canvas right next to it. And what that does is it creates a line, right? There's a line right here as I'm looking down where on one half I can see the image, and on the other half I can see the objects. So what that does is it gets the light of the image exactly next to my canvas. You can do this with a photograph if you're painting, but they didn't have photographs at the time. So this allows me to match colors, right? Our eyes are not good at seeing absolute colors, as I showed you. We only see colors through contrast in the same way that we see black and white. But our eyes are extraordinarily good at matching colors. If you don't believe me, patch a hole in your wall with some paint that's from the garage from a few years ago. It's always going to look a little bit wrong, right? We're always good at seeing how colors don't exactly match up. Okay, so the image, I think the diagram kind of helps, but I think it's more helpful to sort of jump into a video. So this is actually my first watercolor portrait. I'm not an artist. I'll say that ahead of time, and I'm going to show that in a second. But this is the way we set it up in the lab is we made it a little bit easier on ourselves. We're not Tim. We didn't want to make this difficult, but we wanted to do the exercise. So what we have is I'll hit play, and I can talk about it while I hit play. So off screen above you is a computer monitor with a photograph of my daughter, which is upside down and flipped. So when I look down at the mirror, you can see her image, and then right next to her image, you can see my painting. And you just go in there carefully, and you just kind of move your eyes around, and you match, well, if you're good, you can match the colors. If you're me, you just hack at it a little bit for a while. And I was really proud of this, right? It looks kind of like her. But it's my first portrait. I showed it to some artists. They're like, why did you use black? What are you doing? There's plenty of critiques to be had about this, but it was a really fun exercise. And this is Kristen's one. Actually, I want to show this one. Kristen's an amazing artist, and we were sort of learning this. But you can see that there's a few little mismatches in her. I mean, she's way better at color than I am. She's way better at mixing colors. But the perspective isn't quite right on hers. And the reason for that is you have to be really, really careful about your distances. If I go back, if I don't get these two distances to be exactly right, my image will be floating above my canvas or sinking below my canvas a little bit, and now there's parallax. But if I get those images exactly right, there's no parallax, I can go through it, and I can create this again. And what I got to say, this is a really fun exercise. It's really meditative to do this, and as sort of a person who appreciates art but has never been trained in art, it deepened that appreciation. It also sort of taught me the right way to paint. You start to see bigger fields and bigger things of color, and then you work your way down onto finer and finer details. And I've shown this to a few painters, actually. We've done it with a studio art class. And it really does help improve your painting. Okay? All right. So, and I should say one more thing. The color matching that you do should be impossible, right? So I want to go back to this Vermeer. So since Vermeer was actually able to match all the color of all the image here, he was doing it by actually matching the value and the hue. Remember, that's not how our brain interprets color. Our brain only interprets color through contrast. And if you were to actually paint this as an artist and try to get that same effect, there's no way you would be able to get the relative value and hues from some region over here and some region over here to be the ratio that you see in a photograph. Because your brain can't process color over those distances. It only can see color contrasts in adjacent places. But if you're trying to exactly sort of be a dot matrix printer with your little paintbrush and match these things, then you're going to get it exactly right. And in Tim's analysis, he does show that Vermeer and he both got this whole color across the whole thing correct, which is something that no human brain is actually even able to do. It's against the hardware of your brain. So that's some pretty strong evidence that he was doing it. Okay, so I'm almost out of time, so I want to just sort of wrap up to talk about what we've been doing since. So this has just been a fun idea. We've done this project now with 3 different courses and in one public thing. So we've done it in an optics course where I just said, well, one of our labs is going to be, we're going to reproduce drawings, and we did the Vermeer, as we like to call it. We've done it with a studio art class at Pomona College and with Victoria's art history class. And what's really cool about it is every one of those audiences has loved the exercise, right? It's a really fun thing to do. As a scientist, you can take this idea and you can go as far as you want on sort of the optical instruments and forming images and things like that and analyze things. I promise you there's hundreds and hundreds of paintings out there that you can get high-resolution images of that haven't been analyzed yet for the optical instruments that were used for them. But the painters like to do it because it sort of helps them understand how to paint. So I think it really gives the artist an appreciation for the science because they actually can really start to appreciate the power of this optical tool, and it gives the scientist a greater appreciation for the artist. In fact, I got to say, when I first learned of the Hockney-Falco hypothesis, my impression of the sort of Dutch masters of the 1600s kind of went down a little bit. Now that I've tried to do this myself, my impression of them has gone up even more than where it started at. So it's no small feat to any of us can tell if 2 colors don't match. I venture there's not many people in this room who could actually mix them so that you can fix it, so that you can get it to match a little bit. Do you need to add a little yellow? Do you need to add a little green? That's hard. That's the genius. And this is also a really slow way to do it that no artist today would ever create paintings. Of course, why would you? You can take a photograph. But also, it took Tim 4 months to make that painting that was about this big. Okay, maybe that also explains why Vermeer has, I think, 28 works that we know of in his entire life. Okay, so now we've done this with a bunch of people. We know this works. We're actually gearing up for the spring of 2021 to teach a full semester course on sort of optics and art in Renaissance times, and it's going to be team taught by the 3 of us. And we have a couple other ideas that we want to explore. So it's just going to be a whole course of us having fun, really. And exploring these ideas in sort of a hands-on way. So here's another painting that we want to sort of unpack. I haven't read much about this one. This is Hans Holbein, The Ambassadors. So it's, again, one of these photographic images of these 2 ambassadors with a bunch of stuff. And then there's this weird, really misshapen skull right in front of it, if you look kind of carefully at it. If you look at that skull at a glancing angle and from above, the perspective of the skull pops right out and it looks real, and the painting looks like the wrong perspective. I guess the idea was, or what art historians think, is that this painting actually hung on a stairwell. So as you were walking down the stairwell, the skull would sort of jump out at you and scare you. But then if you're looking at it from the big room, you would just see the ambassadors. Okay, so how was this made? Maybe a tilted mirror. I imagine there's going to be a depth of field questions about that. So we're going to try to reproduce some of these anamorphic images. Another really cool thing that Victoria has sort of turned me on to is these perspective boxes. These are made by Samuel von Hoogstraten in 1600s. There are 4 in the world. And what they are is he just took a box and he painted the inside 5 sides of a box, but did each side such that at one spot you could look into that box and you would see an entire room. Right? So this is the front of the box. So this is at a museum, the Detroit Museum of Art. If you put this front onto the box, light can come through that top hole. And then you've got this little peephole that you look through. And they have a reproduction of it that you can use in the museum, where if you look into this peephole, this is what you see. You see this real 3-dimensional image that's really seamless. You're looking at corners and things like that. In fact, I think you can almost make out the corner right there. But it really works perfectly only at this perspective. How did he do this? Well, we don't know, but we're going to try a bunch of ideas and see if we can learn from that. Okay, so I think I'm out of time. So just want to give my conclusions. even with optical tools, I would say making a good realistic painting is still very hard. So we shouldn't discount the masters for using these optical tools. You know, that's what good artists do. They use everything available to them to make better art. And for me, by using these tools, I've helped to gain an appreciation and insight into how painting and drawing techniques. I think these exercises are really wonderful for bringing together artists and scientists in a way that's really approachable and levels the playing field. I think really they learn from each other in one of these situations where it's not the scientist teaching the artist or the artist teaching the scientist. I think we're both learning together. And stay tuned because we're going to try this as a full semester course in about a year from now. Thank you very much.
Okay. Am I on?
Yeah, it's very muted.
You can hear? Okay.
I think I can hear you.
I was really worried when I got the invitation to speak. If optical sciences needs me to talk about anything in optics, you're really in trouble. The last time I was exposed to any academic aspect of optics was in 1952 when I was a sophomore in college, which is not only before you were born, but before your parents were probably born. And I understand things have changed a little bit since then. My background is in chemistry. I graduated from the Polytechnic Institute of Brooklyn in New York. I started going west to the University of Illinois, where I got a PhD, then to Caltech, where I was a postdoc, and then faculty member at the University of California, Berkeley. And then I decided to come down here in 1960. And the reason I did so was that I'd learned something along the way, that it's much more satisfying and stimulating to plant a garden than to confine yourself to mowing the lawn. And so many academic activities can easily dilute themselves and become a mowing the lawn kind of academic enterprise rather than creating something of yourself.
Good to go?
Okay.
Or you can use this clicker to advance.
All right. So how did I get involved in optical sciences and that kind of venture? And it happened in 1971 after I became president. The University of Arizona had a very fine astronomy department for a long, long time, but they had a tough time competing with places like Caltech because there was never enough money around to build a large telescope, which is what you really need to get into the cutting edge of the business. And we got a science development grant in the 60s. We built the Bach telescope, which was a 90-inch telescope out at Kitt Peak. And that was a big advance, but it still wasn't really big enough to play with the big guys in the field. At the time, we had a faculty member, his name was Aidan Meinel. You might recognize that name. Aidan had 6 mirrors from a failed project that were 1.8 meters in diameter. These were lightweight mirrors. And he came up with a clever idea. He said that, you know, we ought to be able to put these 6 mirrors around a common axis and get the effect of a very large telescope. He talked to me about it and other people in astronomy, and we thought, hey, that's an interesting idea. So I went to the legislature, my first year as president, and we got a $2.5 million grant to begin this particular project. And you can see actually the results of that up there. Now, to get funding for this, we needed more money than that. And so we went to the National Science Foundation. Ray Wyman, who was head of astronomy at the time, and I went, talked to the head of the astronomy division of the NSF, and he started to chuckle, saying, no way. There's no way you can possibly combine the light from 6 different mirrors to get a decent image, and turned us down for funding. But he felt a little bit guilty because he knew that we had some pretty good people out here. So they gave us a small grant to do some tabletop experiments. Well, we went ahead anyway, and out of that, we polished 6 mirrors, put them on top of Mount Hopkins, and it turned out that the images we got from that telescope were better than any other images that had ever been made at the time. And the reason for that was really quite simple. The technology to bring all those reflections back to a point was enhanced by computer technology at the time. But furthermore, these were very thin mirrors. And the problem with mirrors is that you've got to get equilibration with the atmospheric temperature if you want to get a good quality image. The Russians had built an 8-meter mirror. It was so thick, however, that the equilibration time could never be achieved, and you could never get a decent image even out of a mirror that large. This became the paradigm then for the construction of every single large telescope that's been built since the 1970s. And that was a piece of ingenuity that optical sciences should be quite proud of. Well, what doesn't stand still? This is the MMT today, the multiple mirror telescope. Still call that, but it's got one whopping big mirror in it. And how did that come about? Well, there's a faculty member by the name of Roger Angel at the University of Arizona, and he was fascinated by the challenge of making large mirrors that were also lightweight. And the reason you want them to be lightweight is you want them to be able to equilibrate with the atmospheric temperature very rapidly. Roger knew that bees had very strong structures because they created combs that were out of hexagonal combs, honeycombs. And he came up with the idea of having a honeycomb structure to support the mirror. Furthermore, he remembered basic physics. If you take a glass of water and begin spinning it very rapidly, the surface goes to a parabolic shape. And so he came up with the idea of casting mirrors in a merry-go-round with just enough glass to give you about a 1-inch thick surface, and that's what happened. Furthermore, developed clever ways of polishing the surface. A mirror this size, made the way the Palomar mirror was made, would take 200 years to polish. This was done in less than 6 months, polished to this perfection. Now, this is the same dome that you saw on the previous slide. But you notice up on top there, there's this little bit of extra material. Well, we had to partner with the Smithsonian on this, and Roger's proposal was that we make this mirror F1. And they threw up their hands and says, my God, you cannot make a mirror at an F1 focal ratio. But Roger insisted that he could. Well, we finally compromised and said, all right, we'll make it F1.2, but then you're going to have to add a little bit of height to the dome because it's going to have to be a little bit bigger. And they agreed to pay for the extra money to elevate the dome. This mirror was made and dedicated about 1980 or so, and it's an absolutely superb mirror. It's still called the MMT, but it's now a single mirror that does exactly the same kind of job. It turns out that the most expensive part of a telescope project is not the telescope, it's the housing for it, the dome that you have to build. So this was a big breakthrough, and it's now led the way to all future telescopes at sea. All right. Well, I left the university in 1982 to head a science foundation, which I did for about the next 30, 40 years, research corporation. About 1987, 88, I had a visit from the head of the astronomy department. We have a project called the Large Binocular Telescope, which was going to take 2 of these big mirrors, put them together, and put them on a common mount. And this would be a telescope that had the ability to go ahead and actually image stars around distant, image planets around distant stars. they got into trouble. And the reason for it was this is Mount Graham, and Mount Graham was home for the red squirrel, and the red squirrels were considered an endangered species, and so years and years of battles began with the environmentalists. The red squirrels have prospered since then and done very well. There's been no problem, but it did create problems. Ohio State was one of the partners we had. They dropped out because of the pressure, so the project got into trouble. Not enough institutions were coming up with their share of the dough. Research corporations stepped in, and we, in fact, salvaged the project, provided the additional capital, got additional capital later on, and the Large Binocular Telescope is operational, and it's been one of the extraordinary. This is a lousy picture, but this shows you the mount with the two telescope mirrors, and it's made some astounding discoveries. Okay, I've told you more than I know about astronomy and optics at this stage of the game. But as was mentioned, I do in fact pursue photography and the use of optics in that field. And as your previous speaker talked about, devices have been used by painters and sketchers for a long, long time. The reason photography got invented was because a man by the name of William Henry Fox Talbot, a Britisher, was well-to-do and went on the tour of Europe with a family after graduation. He was married, had a mother, and they took devices like this device on the end there along with him, which is what people did in the early 1800s. You couldn't buy photographs because photography had not been invented, but you could, in fact, take this device along, put a piece of paper on top, and sketch the scene. And people would take their drawings back home with them, color them in if necessary, and this would be your album. Well, it turns out that Fox Talbot's mother and wife were very good at sketching, but he was dreadful. And there are pictures that he created that you can see in his home at Lake Hawk Abbey. Well, he decided, you know, I'm seeing all these really nice pictures, essentially, that are projected on the ground glass of this device, but there ought to be a way of trying to make those images permanent. And he began exploring the use of chemicals. Silver was known to darken on exposure to light, and ultimately came up with the photographic process in 1839, about the same time that Daguerre in France invented the daguerreotype. Well, this gave rise to a new kind of occupation. Whoops, what happened here?
Just press the same button again. Yeah.
Okay, and these are some of my photographs. And the question of what is a photograph is something that I wrestle with. People are taking so many images with their iPhones these days and what have you that they call photographs, but they're not really photographs, they're pictures. A photograph is an image that I believe has to be printed on paper and framed and looked at. Otherwise, it's just a picture. And I came to Tucson with a camera and began photographing local scenes early on. This is a typical desert photograph, the kind of thing that one likes to do. This is Yosemite after a snowstorm. These are the Harding ice fields in Alaska. This is the top of a mountain that is about 3,000 feet tall, but they're totally buried in snow, and all you see is the mountaintops. Incredible images, actually. I have a whole bunch of them. Texas Canyon, which is just down the road from us. And because of my interest in photography, we invited Ansel Adams to have a one-man show. Ansel Adams had been on the cover of Time magazine, probably the best-known photographer by far in America, and invited him to have a one-man show, which opened up in 1974 at the University Art Museum. And I was young and naive. 10 minutes into the show, I said, Ansel, wouldn't you like to give your archives to the University of Arizona? He choked a little bit and said, well, Berkeley thinks they're getting my archives, but they're just going to bury my stuff in the basement of the Bancroft Library. If you'd like to do something on a grander scale with photography, I'd like to talk to you. So this was exactly what I had in mind, actually. He invited me up to his home a month later. We talked about photography, pointed out that there were a lot of great American photographers who had reached an age, 70, 75, where they were no longer really active promoting new stuff, but had colossal amounts of material, photographs, negatives, correspondence. They had no idea what to do with it because universities weren't collecting photography as an art form. So he said, if you want to think about doing something on a grander scale than just my work, let's do it. And out of that conversation came the Center for Creative Photography, which opened then in 1975 in the summer. And it is now the largest collection of photographs, of American photographs in the world. It has the archives of virtually all of the great American photographers of the 20th century. And it continues to grow and expand, and I hope that you'll have a chance to get over there sometime and look at it because it's pretty extraordinary. Ansel, in 1952, did an essay with Arizona Highways, and it was on San Javier del Bac. And this is, I think, America's most spectacular mission. This was built in the late 1700s, and there was almost no population in Arizona at the time. This was built on the Indian reservation, and it's a spectacular place. Ansel and Nancy Newhall did a nice booklet on this, and I got a call from the mission in 1976 saying, we're all out of this publication, and we really need something for visitors. Could you call Ansel and ask him to have it reproduced and more copies of it made? I called him and said, I'm sorry. He said, I can't do this. I just sold all of my publishing rights to Little Brown, and there's not enough of a demand for this kind of publication to justify a republication of it. Why don't you do it instead? Well, I hadn't thought about that. I'd had some training in photography. I'd gone to art school and learned a little bit about it, and I went to one of Ansel's workshops. I said, all right, I'll give it a try, and I promised myself that I would never take any of the pictures that Ansel took, so that was my challenge. And this is one of the first photographs I took at that time. This is the mission from the front. I personally believe this is the best picture of the mission ever taken, but I'm prejudiced. And these are more detailed looks. Ansel looked at this picture and said, oh, I wish I'd taken that. And that was the best compliment I could ever gotten. This is an amazing place, lots of statuary. I learned to photograph people this way. They gave me a key to the mission. I would go out in the evening after my day at the university and photographed the statuary. And if it didn't come out right, I'd go back the next night. Unlike my children, they didn't bitch and moan about the fact that, Daddy, we don't want to pose again. So this was a good way to learn. The big wolf spider up in the upper right was what fascinated me about this this image. This is one of the friars out there. The kind of handle and ironwork on the door. You can actually still see dents in the door from arrows that the Apaches left when they raided these villages in the early 1800s. That led to an invitation later on by someone in the anthropology department to go and photograph Tarahumara Indians down in Mexico. This is an extraordinary place, actually. It's about as far from Tucson as the Grand Canyon is, but it's a very different kind of country. It is very much like Grand Canyon country. A lot of Indian tribes that live down there. And at Easter they have a fabulous celebration, all kinds of dancing. These are portraits of some of the people. One thing I learned is that if you want to take pictures of people, take along a Polaroid camera, which was what I had in those days. I'd always begin by photographing with Polaroid and giving the folks pictures of themselves. It made things a lot easier, and it was a way of essentially appreciating the fact that they would sit down and let me take their pictures. Very handsome people, great runners. These are people who run, and they've been world-class runners ever since they were discovered. There's a young lady running and two of them resting after a run, but they will typically do races of 30 or 40 miles and have appeared in the Olympics. This is the way they live. Some live in the cave. Some live in log cabins like this. Quite primitive. A little dangerous to go down there these days because of drug trafficking, but this was in the late 1970s and things were a lot more comfortable in those days. Basket weaving, grinding corn, making pots. And out of this came a book called Tarahumara, where night is the day of the moon. The prose was all by Bunny Fontana, who was in the anthropology department here. I accused him of captioning my photographs. He accused me of illustrating his prose, but it was a nice standoff. This is a scene from a wall in Tucson, and it's either graffiti or ephemeral art. I call it ephemeral art. If it's on the wall of my house, it's graffiti. If it's on the wall of somebody else's house, it's ephemeral art. But there's an awful lot of this stuff all around the world, actually, and it is the voice of people expressing themselves in a way that they don't ordinarily have an opportunity to do so. And so I've just been photographing this. I've got a colossal collection of graffiti images. This was from Prague, across from the British Embassy, and you can recognize some of this. And it was really interesting to see how young people were expressing themselves during communist rule in Hungary. No arms for anyone. And I began, as I traveled, I always photographed, and flora and fauna were two things that really interested me. This is grass covered with hoarfrost after a frosty morning, and I've always liked this. And these are some of the interesting kinds of plants that live in the desert environment. I began photographing plants because they're accessible and I could do it in my spare time. Fibonacci series over on the left side, quite evident. And I always consider myself a black and white photographer, and these are all local kinds of plants. Then these silly things started to bloom one spring. I started this in the winter, and the colors were absolutely spectacular, and so I decided, well, I really needed to get into color photography. And so I began photographing local plants. This is Queen of the Night. This is the Arizona local flower. This is a rare kind of plant. I mean, it grows like a dead stick most of the year, blooms one night. It blooms only when the sun goes down and wilts in the morning. The reason this is unusual, it has an incredible perfume. Most cactus plants don't have any odor at all. They attract pollinators by the color, which is why they're so vivid colored. And each one has a spectrum that attracts a particular kind of animal. but these are some of the plants I've photographed over time. The colors really are phenomenal. And those are the flowers that were mentioned, became the stamps. There were 420 million of these published. How many faculty members have a request for reprints of that magnitude? One, okay. So these were issued last February, and it was a real kick to have these out there all around the world, maybe sharing a bit of Arizona and what they look like. So that was good. Lately, because of my personal situation at home, I've got to stay close to home. And so I've been photographing hummingbirds as they come into my yard. And this has been a real kick. And it's also been a real challenge because their wings beat 120 times per second. And that's awfully fast. So I've had to learn how to photograph these things at high speed. And I've now got a flash set up, so I'm photographing these at about a 30,000th of a second, and that's working well. The problem is I get a yield of about 1 out of 10 decent, maybe 1 out of 100 that's really pretty doggone good. And so I've tried to go high tech and get something that will break a light beam. Went out and invested in something that was supposed to be the answer to a maiden's prayer. And it works great in my dark room, but as soon as you take it out in the sunlight around here, it doesn't work anymore. So if you guys can help me out on that front, I'd really appreciate it. There must be a solution. Meanwhile, I'm developing the fastest thumb in the West in terms of clicking off images. And these are all some of our local hummingbirds. We have 12 hummingbird species in Arizona, which is as many as you get. And I still like black and white photography, so I'm doing more and more of these in black and white images. I am trying to catch them in flight, which is the challenge because everybody sees pictures of hummingbirds sipping away at flowers, but that's been done, so I'm trying to do something that's different. So that's my story. Thank you for listening. Thank you for coming to the University of Arizona to visit with us. I hope that we'll see you all back here on a permanent basis in the not too distant future, because it's a great place to get an education, a great place to learn from faculty members who really eat, live, and breathe what they do day in and day out. And I hope that this visit has introduced you to the campus and will whet your appetite and get you thinking about coming back. Thanks.